Let's introduce the Fourier transform by developing some intuition. The Fourier transform is what a Fourier series would become. In fact, it's what the Fourier series spectral plot becomes as the time period becomes infinitely large. So recall, for instance, this big limitation of Fourier series, that it only works for periodic waveforms. And let's say you wanted to take a Fourier series, but it wasn't periodic. It looked like this. Well, one could say that in fact it is periodic. It's just that this distance here, it's just the limit as that time period goes to infinity. So it's sort of a smart alecky way of saying we can say anything's periodic just with an infinite time period. I wrote a MATLAB program that simulates this. Here on the left, this is in the time domain, and this is a periodic waveform, periodic square wave. On the right side, we've got the spectral plot of the Fourier series coefficients. So if you were to analyze this in terms of A sub n's and phi sub n's, this is a plot of its A sub n's. So just to take a couple as an example, at DC, looks like this is always 0 or higher, so it makes sense it'll have a non-zero DC value. It goes up to 1, but it only goes up to 1 for about perhaps 20% of the time. So its average value would be 20% of 1, which would be about 0.2, and that in fact is what that DC value is. And its fundamental component is the strongest, and its second and its third and its fourth and fifth harmonics are as shown. Now below is the same waveform. This is in the time domain. This is its spectral components of its Fourier series. But this slider will pull the time period apart. So as we increase the time period a little bit, you can see what happens to our spectral plot. It's almost as if we take this original spectral plot and we start filling in these values. And that should make sense because as we increase our time period between the two, our fundamental frequency has to get smaller since our fundamental frequency is 1 over the time period. And sure enough, when the time period is twice as big, our fundamental frequency is half as big, and it starts filling this in. As we continue to make our time period larger and larger, our peaks get further and further separated. We continue to fill in our A sub n values. And now we can only see one full pulse. The other one is almost off screen. These discrete values have become almost continuous. And when we reach that limit of t goes to infinity, we get the Fourier transform. So this is no Fourier transform, lots of discrete values, Fourier transform. Now instead of being discrete values, it's a continuous waveform. Instead of it being an infinite sum of harmonics, it's now an integral of these different waveforms. So we've got a differential amount of this frequency and a differential amount of this frequency and a differential amount of this frequency that when added together produces that waveform. And just like the Fourier series can be broken down into magnitude and angle, and I've shown you the magnitude here, we could have just as well done this showing how the angle also goes from being discrete values to a continuous waveform. One unusual thing we do with the Fourier transform is we make it dual-sided. So this is the way the Fourier transform is usually shown. It's the same thing as the single-sided, just the continuous version of our single-sided Fourier series, but we're going to mirror it around the zero frequency point. Now mathematically, that should make sense to you, because how much energy does the signal have at negative 2 Hertz? Should be the same as it has at positive 2 Hertz, since cosine of negative 2t is the same thing as cosine of positive 2t. But the question then is, why are we doing it now for Fourier transforms when we didn't do it for Fourier series? The answer is that it will help us understand a topic we'll cover shortly called amplitude modulation, which will sound like magic, but the Fourier transform makes the math just fall apart and lets us see how we can modulate multiple signals, like multiple speech signals, onto the same wire at the same time.